In this clip, I'm assuming that you already have learned how to calculate torque. Now we will start by looking at the conceptual question. A 90 centimeter long bar of 1.2 kilogram can rotate in a vertical circle around a frictionless axis set at its end. If the bar is released in the position shown in the picture, what happens to the torque due to the force of gravity in the moments that follow the release? So we have the bar in here, there's gravity that is acting on it, and we want to know what will happen to the torque due to gravity as the bar is released. So 1, the torque will increase, 2, the torque stays the same, or 3, the torque decreases. Hit pause and try to think about it on your own, and then you can come back once you have your answer. First, we have to think about where is the force of gravity acting on the object. Is it on the tip, at the pivot? Actually, it is applied at the center of mass of the object, and the center of mass for a rectangle is just in its middle. That's the easy part. The way to think about this is maybe to imagine what's going on when the bar is just lower, a little bit lower, okay, so after a few moments. And again, the force of gravity will be acting in the middle of the bar. So you can see that the angle of the bar is a little bit smaller than it used to be, and this will have an impact on the calculation of torque. So let me just move the angle in here so that it's not in the way. And we can think of this in a couple of ways. Maybe the easiest way to see it is using the lever arm or the moment arm of the force applied. So if we wanted to calculate torque, we could just draw the R vector that looks like this in both cases. And this R vector will be actually the same length in both cases, both for the picture at the top and the picture at the bottom. But we can then try to draw the moment arm. The moment arm, I remind you, is what we get when we extend the force by its line of action. So we can do this for both. And once we extended the force by its line of action, we want to find a line, the shortest distance essentially, between the pivot and where that line of action is applied. So in the case in here, the moment arm would just be this distance in here, while in the second case, it is this line in here. So these are called differently depending on the textbook. I like the notation R perpendicular because it really shows that it's perpendicular to the line of action. Some textbook will use D as well. Then, to calculate the torque, we just need to take the moment arm, R perpendicular, times the magnitude of the force F. That's it. So in here, if we compare situation A to situation B, you can see that the R perpendicular at A is actually smaller than the R perpendicular at B. This is because a larger portion of the vector R is now an horizontal component in the second case. And we know that the R vector itself is always the same length since it corresponds to half of the length of the triangle. So since we have that relation, we can conclude that the torque due to the force of gravity in case B will actually be greater than the torque due to gravity in case A, and therefore the torque is actually increasing in this situation. This means that the torque due to the force of gravity is not constant. As the object rotates, that torque will keep changing. So when we look at these type of problems, often we will calculate the torque at one given orientation of the bar, and that's the only thing that we can do in these cases. So that's actually the problem that I want to look at. Here we still have the same bar, 90 centimeter long, 1.2 kilogram of mass, rotates in a vertical circle again around a frictionless axis set at its end. The question is, what is the angular acceleration of the bar at that moment? So just as before, we have to deal with the force of gravity. So we have that one in here. And in addition to the force of gravity in here, to make it a little bit more interesting, I also added a force applied. So what I want to find in here is what will happen with the rotation of the bar under the influence of these two forces. So I encourage you to try to solve the question on your own and then to come back. The idea is to find the angular acceleration and link it to the force. We have to use a mid step or an intermediate step, which will be to calculate the torque, because it will be the sum of all the torque that will be responsible for the angular acceleration. And we know that the two are proportional. And the proportionality constant that we'll have between the two is usually labeled I, and this is called the moment of inertia. And the moment of inertia is really just a measurement of how much resistance is the object offering to a change in the rotation. So it plays the same role as what mass is doing for translation, but now we're looking at rotation. So in order to solve these kind of problems, the first thing is to identify all the forces that are present on the object. And here we already have the force applied in the FG, but we're missing a third force that will be applied at the pivot. So our goal is to calculate the torque due to each of these three forces, combine it together so that we can then find the angular acceleration. So let's start by calculating the torque due to the force of gravity. The easiest way to go is probably as we did in the other question, to just look for the moment arm. So let me just move this on the side as we did before. And really the goal is to realize that what we're looking for is a line that will pass through the pivot and that will be perpendicular to the force. So the R perpendicular, the moment arm, is just this line in here. And since we know that the R vector is just in here, and the R vector is a length that corresponds to the length of the bar divided by 2, and we know that the angle in here is of 37 degrees, then we can see that R perpendicular will simply be equal to the value of the length of R times the cosine of 37 degrees. So we'll get for the torque due to Fg just R perpendicular for Fg times the value of Fg itself. So the R perpendicular once again is L over 2 times the cosine of 37 degrees in here. And then we multiply this by Fg, which is just mass times acceleration due to gravity. So once we plug the numbers in, we'll get the length of the bar, which is 90 centimeters, so 0.900 meters divided by 2, times the cosine of 37 degrees, times the mass, 1.200 kilograms, times the acceleration due to gravity, 9.80 meters per second square. And when we plug all the numbers in, what we'll get is 4.23, and we get kilograms meters per second square. That's just a Newton times meters, so Newton times meters. Also, you see that the force due to gravity is trying to rotate the object clockwise, so this will bring us a negative sign in here. If we want to be super explicit, we can draw next to the sum of torque an arrow pointing this way with a positive sign that tells us that counterclockwise is what we decide is the positive direction. Next is the torque due to the applied force. And to find the torque due to the applied force, I'll try a different method. So we know that the R vector for the applied force will actually be in green in here. So it's all of that. And you can see that it extends on this side, and that the angle that we would be looking for between the R vector and the force is actually the angle on the other side. So if I redraw this in here, we would get the R vector that is pointing this way, and then we have the force that is pointing this way, and the angle between the two that we're looking for is not the 60 degree that was the one perpendicular to the bar, but rather we want to use the 30 degree that is the angle between the two vectors. So we can just take the length of the R vector, which is the full length of the beam, times the magnitude of the force applied, and then times the sine of the angle between the two, and that angle is just 30 degrees. So once we put the numbers in and we do the math, we'll just get that we have the full length, so the full 0.90 meters, times the force applied, 5 newtons, times the sine of 30 degrees, which is just 0.5. And once we do the math, we will get 2.25 Newton meters. And this one is trying to rotate the object counterclockwise, so therefore it will have a positive sign. Next in line would be the torque due to the force applied, or the force at the pivot P. And for that one, we could find the moment arm for the force P times the force P itself. But you can see that the moment arm for force P is just equal to 0, since it is a force that is acting right at the pivot. So this torque is just not contributing to the sum of torques. So the only piece that we are missing and before we can finally calculate the angular acceleration is to calculate the moment of inertia. So for the moment of inertia I, here we have a bar that is rotating around its end. So you want to go in the tables, and in the table you will see that you have for the bar rotating around its end 1/3 ml squared. So we can just plug the values in there. So we have 1/3 times the mass, 1.200 kilograms, times the length of the bar, 0.900 meters, and this one is squared. And you can see that the moment of inertia of the bar will be 0.324, and this will be in kilogram times meter squared. Finally, just allow me to give myself a bit more room. Finally, we are ready to put all of this together. So what we want to do next is just to do the sum of torque, as we said. And the sum of torque in here really has two contributions. That will be the minus 4.23 newtons meters, and then plus the 200.25 newton meters that is coming from the force applied. So the net torque will just be equal to minus 1.98 newton per meters. And since we know that the net torque is equal to the moment of inertia times the angular acceleration, we can see that the angular acceleration will just be equal to the sum of torque divided by the moment of inertia. So if we put the numbers back in there, we get minus 1.98 newton meters divided by 0.324 kilograms meter squared. And this will give us the value of the angular acceleration, which will be equal to minus 6.11 rad per second squared. All right, you see the rad comes from the fact that we have a cancellation of the units, so we essentially just get 1/second squared, so we add the radian in there to make it clear that it's an angle. So the negative in here tells us that the angular acceleration is actually pointing in the clockwise direction, just as we would expect, since the Fg in here has a contribution from the torque that is larger. Now, I want to know how the angular acceleration of the bar will change if the pivot is actually set at the center of the bar. So it's the same applied force as before. And I want you to tell me what will change, essentially. The problem is a bit simpler, mostly because the force due to gravity is now acting at the pivot. So both that force as well as the force due to the pivot itself are acting at the same point, which is at the pivot. So when we focus on what changes and what does not change, well, first we can see that the torque due to Fg is now equal to 0, while the torque due to the force applied at the pivot will also be 0, just as before. In other words, this means that now the sum of torque is due to only one force, which is the torque due to the force applied. So it will be fairly easy to calculate this. However, you have to realize that torque due to the force applied, which is equal to just the r vector times the force itself times the angle between the two, will be slightly different, because previously we had that the value of the torque was just the length times the value of the applied force times the sine of 30 degrees. Although the angle does not change, the length of the r vector is divided by 2 because of the new choice of the pivot. So the torque that we'll get from the force applied will now be equal to 1.125 newtons meters, so half of what it was before. So after this, we can look at the angular acceleration by again thinking of this in terms of sum of torque divided by the moment of inertia. But the moment of inertia also changes, because the new moment of inertia has to be calculated using the formula for the moment of inertia of a bar around its middle. So this will be 1/12 ml squared. So this will be 4 times smaller than the previous value. So it will be 0.081 kilogram meter squared. So in the end, we can recalculate the angular acceleration, and it will just 1.125 newtons meters divided by 0.081 kilogram meters squared, and we get the value of 13.9 radian per second square. So the angular acceleration indeed increased in here. So be aware that when you change the location of a pivot, you will have changes not only to the torque but also to the moment of inertia, and that your angular acceleration will likely be a different value. Thank you for listening. Hope to see you again.